Hello, I'm Zhixin Xia from the School of Physics, Nankai University School of Physics, China. And today I'm going to talk about the Whirlpool in a bottle. And these are the contents. They are problem review, pre-experiment, theory, experiment, and conclusion. And the first part is problem review. You can pay attention to the video on the right. When an open bottle of water is turned upside down and slightly rotated, a whirlpool is formed. And what are its characteristics and how fast can the bottle be emptied by that way? What will change if the bottle is filled with sand instead? The keywords I extracted are slightly rotated and the characteristics, how long, change, and sand. Then is the second part is pre-experiment. And these were our apparatus. Okay, and these are the comparison between irrotational and vertical water. Okay, and replace the water into sand, and we'll find something. Oh, I'm sorry. We'll find something different. And the third is it is a interesting phenomenon. There were lots of water left, but sand didn't. And according to our pre-experiment, it can be easily found that for same liquid, a vertical one falls down faster than irrotational one, and the larger hold the faster volume flow rate. And comparison of water and sand will find that the volume flow rate of water is much bigger than sand, and if the diameter of the hole is not big enough, there will be a lot of water left, but sand will still fall out. And we can't keep the sand spinning like water, and the stable process is not completely uniform. I think probably we think it is the water is a communism and no tangential force in sand. And some related physical quantities can be easily found that a diameter of a hole, diameter of bottle, viscosity coefficient of liquid, angular velocity of rotation of liquid, initial height of water in the bottle, and gravitational acceleration. I think they are the related physical quantities. And the third part is the theory analysis. The whole following process of a vertical liquid will be divided into three parts. You can pay attention to the right video. And we'll find that we'll find the outflow of water, and we will find the whole following process of vertical liquid will be divided into three parts. They are the formation of the air excess, and the symbolization of the air excess, and the close of the air excess. And you can compare it into the video on the right. Process 2 is obviously much longer than 1 and 3, and the process 3 is random, and the water surface of liquid left is always lower than 1 point. And here are two assumptions. Replacing the diameter of air excess with an average doesn't make much difference, and replacing the friction factor of head loss with an average does not make much difference. These are true when the measurements are very close to the average. Then we can get the physical model I'm going to describe next. Using assumptions, we can abstract the problem into the red map. We only analyze the time of process 2, and most of the parameters are labeled on the map. Firstly, we get the first equation from Bernoulli's equation of fluid. Physical quantity is not specified in the sketch map. A factor of kinetic energy correction and the friction factor of head loss. The volume is well determined at a certain time, so we can get the second equation, and because of the excess of air, we get the third equation. Solve the equations, we get the expression for T, and T is positively related by initial height and negatively corrected by the whole. And then we came to the sand. The flow of the sand take on a whole new shape, and in chemical engineering, it is called the green flow. And it is found that the JSON model can well predict the stress from only when the side ratio of the container versus the particle is larger than 16. And no matter how high the sand is after it has accumulated to a certain height, the pressure at the bottom is almost constant. And the sand ticks when it falls down. And from our reference, we can get the expression of volume flow rate of sand on the right. Okay, and this is the fourth part, experiment. On the left is the diagram of experimental apparatuses and the bottles used, and on the right are the corresponding parameters of the bottles. There are two main parts to our experiment. One is the black bottle cap experiment. Analyze all of the experimental data in order to verify the theoretical assumptions. And the other is the other bottle caps experiment. Based on a black bottle cap experiment, try to find the relationship between falling time and the parameters. And the measurements are very close to the average. We can see in the figures. So we can prove that our theoretical assumptions about the diameter of the air excess and the friction factor of head loss are correct. Then the measurement, these are the TH curves of white big cap and white small cap. And we can find the relationship between T and H is verified. These are the TH curve and the T whole curves of purple cap. We can see that the relationship between T and the whole is verified. And these are the comparison between water and sand using gray cap. The trends are similar, but the models used are different. The theory is verified, I think. And the fifth part is conclusion. From this problem, we get one is that the Whirlpool is shaped like a long-necked funnel, and the other is that it creates an excess of 4 bubbles to flow in when the water flows out. For the same liquid, vertical one falls down faster than irrotational one. The larger hole, the faster volume flow rate. And the expression of flowing time of vertical liquid is as follows. Comparing between water and sand, we found the volume flow rate of water is much bigger than sand. And if the diameter of the hole is not big enough, there will be a lot of water left, but the sand will still flow out. And we can't keep the sand spinning like water, and the stable process is not completely uniform. The flow of sand takes on a whole new shape, we can't take it same to the water. And that's all. Thank you. Thanks for listening. And here are my references.
Hello, my name is Oleg Avestenko. I'm from Team Ukraine. Now I'm going to oppose the solution of problem number 5, Whirlpool in bottle. According to a statement of the problem, reporter needed to investigate the flow of the water from the bottle, which is rotated, and thus defines the what the parameters define this time. First of all, in the report, the reporter qualitatively investigated the effect of the flowing of the water from the bottle and divided it into 3 stages. Indeed, we agree with them because of, indeed, first of all, the system has to stabilize for some time. Then there's the main stage of the flowing, and then the final stage, which is much lower at the time as other stages. So reporter mainly in his report have to investigate the first stage. Then reporter gave us a demonstration of the effect. We showed his experimental setup. Indeed, it was quite good, but there was some questionable thing about the variation of the parameters of the bottles and the of the bottles and the water parameters. How reporter exactly defines the relevant parameters in the problem, it wasn't clear from the report. Then in theoretical investigations, the reporter wrote down the Bernoulli equation and continuity equation, and our team thinks that there's some kind of problem here because of these equations may be applicable only for non-viscous case, but the problem is that the problem is that for the formation of vortex and its stability, the friction is very relevant, and thus the reporter needed to take the friction into account, but in the report there were no friction terms which were placed inside the theoretical model, which reporter taken into account. Then reporter moved to the Yanis model for the sand. Indeed, it is well-known effect for the pouring of sand that the pressure doesn't strongly depend with the depth, and thus reporter applied well-known results for the description of the pouring of the sand. And then he moved on to the experimental investigation. He provided an experimental setup, but there was a lack of experimental investigation of the following effect because we didn't observe the dependence of main parameters, or for example, the time of the flowing and the other thing depending on the parameters of bottle itself. For example, its height, its radius, the radius of the hole, the height, initial height of the water, and thus the reporter didn't investigate it this clearly. At the end of my retelling, I want to say that reporter gave us really clear and simple understanding of the problem, showed us a demonstration of the effect, and investigated different parameters of the system qualitatively, which were done on a good level. But in the theory, there was a problem with the theoretical model, about which we mentioned during my monologue, and it were related mainly to the friction and other things. For example, to the evolution of the vortex itself, because reporter didn't take into account. Reporter considers the flowing of the water, the velocity of the flowing of the water to be the constant. We do not agree with this, and thus we think that this part of the solution need to be improved. In the experimental part, reporter gave different dependencies of on some parameters, but as I mentioned, there need to be more parameters investigated, such as the radius of the bottle, the radius of the hole, the initial height of the water, and so on. So here are my discussion topics, and I think we can move on to the discussion.
Okay. I will begin. Firstly, I have taken the friction in consider because I use a constant to describe the influence of the friction in my 12 pages that I said that. I consider the friction factor of head loss, and I take the for same bottle and same cap, and we use the same factor of head loss to describe the influence of the friction.
May you clarify which factor did you use? I do not understand clearly.
Okay. I will share my screen.
Okay. I have to stop my demonstration, yeah?
Yes,
Yeah,
you have to stop the demonstration.
Okay.
I mean, okay, can you say it? I mean this factor, this.
Okay, and I understand, as I understand it is the factor which is caused by what? By the laminar flow or the turbulences inside the bottle or what?
It is for the water and for the same bottle and same cap and for the same hole, and we use the same friction factor of head loss to describe the influence of the friction. So I mean I have taken it into consideration, but you said that I didn't. So I want to explain that.
Okay, and does this factor depends on the parameters of the bottle?
Pardon. I didn't.
Does this factor depends on the parameters of the bottle?
Yes, it is divided by it is it is divided by it's decided by the material of the bottle and the material of the cap, and the exact shape of the hole. You know that we can't take the hole there are something not very good on the hole, so it is not.
Oh, okay, as I understand, you haven't investigated this parameter in your problem. Yes?
I didn't show it on my slide, but we have considered it because okay, and
okay, I understand that it qualitatively depends, but you haven't investigated it quantitatively, yes?
I have I didn't yeah, but
okay, I think it would be much better for the problem. Now let's move on to the question about the importance of the initial rotation. Have you investigated how does it affect the whole time of the flowing out?
We just rotated at the beginning of the time because we think it is slightly rotated. So the initial rotated is we didn't analyze if we rotated with very big force and what will happen, because there's a slightly rotated in the problem. So
okay, and do you think this initial rotation, defines the time of the flowing out or not?
Okay. I want to ask because I think it is a very good advice. So I wonder how you consider this question.
About the slight rotation.
Yeah.
I think that we have just to start the vortex, but the parameters of the vortex itself depends on this the starting position, like the strength of the vortex or other parameters, the angular velocity. They both depends on the on how do we using our hands start the motion. And on my opinion, it strongly defines the time of the flowing. And as I understand, you haven't investigated it, and in my opinion, I repeat, it is needed to be done in this report.
Oh yeah, you mean you use the vortex to analyze this question? Do you mean that? Okay, and
we now can add team members to the discussion. Go ahead, just everyone now can participate.
Yeah, and in the clarify, someone asked me that the angular velocity. I have taken it into consideration, but our facilities cannot provide the accuracy of our experiment of the angular velocity. So I want to ask how you measure the angular velocity of the rotation of liquid, and how do you make the accuracy of it? Sorry, can you hear me?
Yeah. Yes.
Okay.
You questioned us about how we define the angular velocity.
Yeah. how to make the acceleration of the angular velocity of rotation of liquid because our facilities cannot provide that accuracy. So maybe our consideration is not a very good idea. So I want you to give us some advice.
Okay, like mainly we think that indeed the initial angular velocity, it depends on the initial stage of the rotation, but like how to measure it, it's a post-factum experiment. Like you will measure the angular velocity after you started the rotation of the bottle. And using this, you define the parameters of the time of the flow.
Oh yeah. I think it is right. So how do you keep the how can you make the accuracy of it? You make many times of the experiment, or you use you use some you use some other things to do that. I mean the accuracy. How can you?
Are you asking us about our experiment? We cannot say nothing about our experiment. We are talking about your experiment. Okay, may I ask you a question about the shape of the bottle and the shape of the hole? As I understand, they strongly defines the coefficient, the friction coefficient, which you just didn't investigate it. Let's discuss how does it qualitatively depends, or how does it defines time?
The definition of my time is from the beginning to the water surface flow down to the point B. You mean you know our bottle it have a big diameter in the bottom and has a small diameter in the top of the bottle. So if we turn it upside down, it will become the it's a bigger diameter on the top and a smaller diameter in the bottle. So because from our pre-experiment we found that there will be many water left, and it is random. So we didn't we didn't take the water surface below point B into consideration. We only take the time before over the B when the water surface is above the B. Yeah.
Okay, I see. And also I want to ask you about the stability of the motion. What defines the stability of the vortex itself? For example, usual vortex which we try to make in a cup of tea, for example, it's very fastly decays. What is the reason of stability in your?
Yeah, I know. You mean that I need to consider take a vortex into consideration, right?
In what manner you think your experiment is reproducible?
Oh, I'm sorry. Our network.
In what manner you think your experiment is reproducible? Because you do it by hands and you turn in a random velocity. And what about the reproducibility?
Did you get the question?
Okay. I mean, you asked me when I slightly rotated the bottle and I take one into consideration.
Yeah.
When I make the bottle slightly rotated and my purpose is to make the Whirlpool. My only purpose is to make the Whirlpool, and if I found that there are many bubbles come from the bottom of the top of the bottle, and
Okay.
I will stop my.
The question is the following: what is the influence of the second lower bottle? Can we just remove half of the experimental setup and still get the same results in terms of time for the bottle to empty. Okay. Can we remove the lower bottle without influencing the results of the experiment?
A lower bottle, you mean the smaller intentional height?
On the video, in the description of the problem, there are two bottles connected together, but you have described the emptying of one single bottle. So does it matter?
You mean I cut out the bottom of the small diameter of the bottle and to make the experiment to do again?
Well, you have shown us the experiment of emptying one single bottle, right?
Yeah.
Right.
Yeah.
Yeah. On the video, in the description of the problem, there are two bottles connected with each other.
Yeah. Yeah.
So does it matter? And will the time of emptying be different in this setup or that one?
It will make a difference because the pressure of the air will not be equal, and there will make a difference. And because I pay attention to the problem, and it said that when an open bottle, so I didn't make too much take too much consideration of the two bottles.
Okay, thank you.
Thank you. Julia, do you have any questions?
Yeah, I have a very short question for reporter team. So what exactly in your model will change if we exchange the bottle for shape of sphere, idea sphere, or to shape of cylinder, very thin and long cylinder? So what will change in your model? Do you understand my question?
Yeah, I understand, but you know, my oral English is not very good, so I need to. I will calculate it. I will cut it into many. In my theoretical analysis, I'll cut it into many.
I mean, quantitatively, without numbers, what change? Like time will be longer or shorter, or be exactly the same, or something?
Yeah.
Without numbers, just quantitatively.
Okay. I finally understand. You mean what will the time change when
Yes.
the parameters changes?
When the shape of the bottle.
Shape of the bottle.
Mm-hmm.
Shape of the bottle, and if the diameter of the bottle, that the bottle
is the same. The diameter is the same.
It's the same. Only change the shape. You mean?
Yes. Yes.
Oh yeah. No. I need to make integral, I think.
I mean, without numbers, just what change? Like become bigger, or what parameters in your model will change?
Model. Maybe I need to change my model into the shape of the bottle, and
so your model is applicable only for bottle your shape that you presented.
My theory is it only I only consider it into cylinders, and I didn't take the different shape of the bottles.
Okay, I got it. Thank you.
Okay, thank you.
Thank you. Leandro, you have time for your question.
Okay, I have actually two questions, but one of them is more important than the other, and it's for both teams. I didn't see any estimation of uncertainty in any of the measurements. Why? Why don't you put an error bar? Why don't you do some data treatment to understand the limitations of your measurements? And what should they be?
Oh yeah, and I get it because I didn't write it on my slides, but you know I make the figures, I make the management data, so I considered I considered what I said on my draft, but I didn't show it on the slides. That's wrong. That's wrong. That's my fault. I'm very sorry for that.
And I have a second question. If you take a bottle and you turn liquid inside it fast enough, due to centrifugal forces, it's going to take longer to flow. So your model doesn't consider this possibility. I mean, the time only decreases with when you create a whirlpool. What should your model include to take into account the fact that the time should go through a minimum and then raise again? And it's for both reporter and opponent.
He asked me the question about what will change if I know. So if the situation changed into what he described, and I think we need to change our model into another format, and we need to take the vortex into consideration, and we will measure the angular velocity of the water, and try to make another model to solve this problem, because this problem is only for the slightly rotated, and he used a very big force to make it rotate. So we need another model to solve this problem.
Yes, indeed, this fact may be observed, and indeed it is important in this problem, and I think that reporter needed to investigate.